All right, today we're going to cover topic 1.16, which is the intermediate value theorem. And a very important word in the definition here is the word continuous. All right. If the function is continuous on the closed interval, that word closed is important, and d is a number between f of a and f of b, then the intermediate value theorem guarantees that there is at least one number c between a and b such that f of c equals d. What are we talking about here? Well, we've covered the intermediate value theorem in pre-calculus. Basically, if you have this function, and here's a, down here is f of a, all right, and over here is b, and up here is f of b, all right. This function assumes all of these y values, every single y value between f of a and f of b. And of course, one very important one, and that's the value 0, all right? So somewhere between f of a and f of b, there has to be f of c, all right, wherever that value is. That's the intermediate value theorem. So let f be a function that is continuous on the closed interval -4 to 3, and they tell us that f of -4 equals 7 and f of 3 equals -1. Notice there's a sign change. That's important. Is there a number k between -4 and 3 where f is guaranteed to have a 0? Well, first, we need to say that f is continuous. So the intermediate value theorem, IVT for short, applies. We need to get used to saying that in the AP calculus world. Since f is continuous on a closed interval, all right, then the intermediate value theorem applies. And we see that f of 3 was -1. Then we had a sign change and went to down to f of -4 was 7. We have this sign change, so yes, there's guaranteed a 0, most definitely. We've got some graphs here, and we want to ask how many of these graphs below represent functions that meet the criteria necessary to apply the intermediate value theorem. This first one is a no because we've got an open interval. The next one is yes because we have a closed continuous function. The next one has a closed interval, but it's not continuous. So this one is a no. The next one is no because we have an open interval. And finally, this last one is a yes because we have a closed interval and a continuous function. All right, keep moving here. The functions f and g are continuous for all real numbers, and the table above gives values of f and g at selected values of x. F and g are continuous. That means a composition of function of those two would also be continuous. So they said h is given by this ugly thing right here. Explain why there must be a value, k, between 2 and 4 such that h of k equals 6. All right, so what we do here is let's try h of 2. H of 2 is going to be 2 times 2 minus g of f of 2. Well, f of 2, all right, is 1. So we're going to have 4 minus g of 1. And g of 1 is 2. So 4 minus 2 means that h of 2 is 2. All right? So then if we try h of 4, all right, if we try h of 4 in our function, we have 2 times 4 minus g of f of 4. F of 4 is 3. So we're going to have 8 minus g of 3. And g of 3 is 1. 8 minus 1 is 7. All right. And there we go. This is h of 4, which is 7. This is h of 2, which is 2. We have shown that there has to be a value that is between 2 and 7. Okay, h of k, there is a value because this function is continuous and the intermediate value theorem applies. All right, let's look at this next problem. Let f be a function that is continuous on the closed interval. K of negative 1 equals 2.
Thank you. Oh, please report down to the
And k of 10 equals 12. Which of the following is guaranteed by the intermediate value theorem? Well, k of 2 equals 7 is possible, definitely possible, because 7 is between 2 and 12, but it's not guaranteed. All right, it's not guaranteed. How about, so this one is a no. Letter B, k of x attains a minimum. Well, it does attain a minimum, all right, but not by the intermediate value theorem. So that one's out. All right. How about letter C? Letter C says k of x equals 10 has at least one solution in this interval. That is true. This is a yes because we're looking at 2 to 12. 10 is between those two values. According to the intermediate value theorem, that is guaranteed. That's our answer. Letter D, we're talking about a completely different interval. We're not talking about y value intervals. We're talking about x values. So letter D is out. All right. Last thing I want to talk about is I want to come back to the limit as x approaches 0 of sine x over x. We've talked about this. We know that's 1. All right, but there's some other important rules I need to give you about this particular function. Another rule we know is that the limit as x approaches 0 of the sine of ax over ax also equals 1. So if I had the limit as x approaches 0 of the sine of 3x over 3x, that is also equal to 1. That's just a verifiable, provable fact. All right? And there's one more. The limit as x approaches 0 of the sine of ax over bx is going to be equal to a over b. All right? And that is one that actually showed up in one of our AP calculus, my AP problems. All right? So let's just consider this problem. If I have the limit as x approaches 0 of the sine of 5x over 8x. This problem showed up. And let's just do a little bit of algebra here. Let's multiply this expression by 5 over 5. If I multiply, which is a form of 1, which is totally acceptable. All right, if I do that, according to the commutative property, I can flip-flop these two numbers according to the commutative property. And so I now have the limit as x approaches 0 of 5/8. Sorry for that interruption. 5/8 times the sine of 5x over 5x. And we know with our rules of limits that I can pull this 5/8 out in front. And look what I have. The limit as x approaches 0 of the sine of 5x over 5x. And we just said that this is equal to 1. So 5/8 times 1 equals 5/8 and we have proven or shown this rule to be true. And that shows up in some AP calculus problems, and I wanted to add that in at the end of our lecture today. So hopefully that helps you with topic 1.16 and some issues with sin x over x. We will stop there for today.